Okay,
let's
let's
just
just
move
move
on to
on
the
to the
next
next
set of
set of
problems.
problems.
So
So,
I think
I
the
think the
best
best
it's
is
problem
problem
solving at the
solving
end
at
of
the
the
end of the
day.
day.
So
So,
looking
looking
good.
good.
So I
So,
think
I
I
think
need
I
to
need
do
to do
this.
this.
Let's
Let's
do
do
diameter of a
diameter of a
binary
binary
tree.
tree.
Let's
Let's
pretend I
pretend
didn't
I
see
didn't see
that.
that.
So
So,
how
how
would
would
you
you
find a
find a
diameter of
diameter
a
of a
binary
binary
tree?
tree?
I want
I
to
want
do
to
a
do a
DP
DP
problem
problem
for
for
real,
real,
but I feel
but I
like
feel like,
oh, I
oh,
don't
I
have
don't
any.
have any. Shit.
Fuck,
Fuck.
I need
I
it.
need it. It pains me to say this.
Okay,
Okay,
this
this
is
is
the
the
shit. I
shit. I
think
think
XOR
XOR
total
total
an
an
array
array
defined
defined
as a
as a
bitwise
bitwise
XOR
XOR
of
of
all of
all of
this
this
element.
element.
Okay,
Okay,
what is,
what is,
for
for
example,
example,
XOR of
XOR of
total
total
array?
array?
This is
This is
2
2
XOR.
XOR.
What
What
the
the
fuck?
fuck?
Bro,
Bro,
18
18
minutes.
minutes.
If it's
If
an
it's an
empty
empty
subset,
subset,
XOR
XOR
will be
will be
0.
0.
If it
If it
is
is
2,
2,
total of
total of
2.
2.
The
The
8
8
subsets
subsets
are
are
the
the
empty
empty
subsets
subsets
have
have
what the
what the
fuck is
fuck
an
is an
XOR?
XOR?
XOR
XOR
total.
total.
I don't want
I
to do
want to do
this.
this.
Backtracking.
Backtracking.
Let's
Let's
just
just
do a
do a
backtracking.
backtracking.
What is
What is
backtracking?
backtracking?
It's
It's
something to
something
do
to
with.
do with.
Okay,
Okay,
give me
give
a
me a
second.
second.
Another.
Decision that you made. So we make decisions, but we know that we're kind of able to undo those decisions. And so together, this is basically called recursive backtracking, where you go and you make decisions and you deal with those decisions, but then you undo them at some point. And generally the reason for doing all of this, it's generally to do an exhaustive search. So it's basically like the definition of a brute force technique. It's basically whenever you are asked something like, if you want to see all solutions. So if you ever see something like all, then you would use something like backtracking to generate all the solutions. Okay, so the best example to explain backtracking would be the subsets problem, where again we're looking for all the subsets. So we're given an integer array of nums of unique elements, and we need to return all of the possible subsets, aka the power set. So a subset of an array is a selection of elements, possibly none, of the array. And the solution set must not contain duplicate subsets. And you can also return the solution in any order. So basically what it's saying here is that if you're given an array of numbers, 1, 2, 3, we need to return all possible subsets. So you could choose no numbers, you could choose just 1, just 2, or just 3. You could choose 2 numbers, so you could choose 1 and 2, 1 and 3, or 2 and 3, or you could choose all of the numbers, so 1, 2, 3. And in total, you'll see here, we actually have 8 solutions. So we're getting 8 because we'll see the math shortly, but since there's 3 different numbers here, and you could choose or not choose each number, you could actually get 2 to the 3, which is equal to 2 times 2 times 2, which is equal to 8 many solutions. So we'll start our solution as empty, so there's nothing so far. And let's say we're considering the number of 1 right now. So since it is subsets, we could either choose that number or we could not choose that number. So that basically means each time we're going to have 2 different branches. So when we draw lines like this, it's really branches of this imaginary tree. So the left path, we're going to represent this left path as basically don't choose. So I'll put an X there as in don't choose the number. And this path will be choose that number. So on this level, we're considering the value of 1. Over here, if we don't choose it, our solution is still empty. And over here, if we do choose it, okay, well then so far our solution is the list of 1. So at this level here, we're considering the value of 2. And so if we don't pick that number, we still have nothing. And if we do pick that number, then we have just the list of 2. And over here, if we had instead picked 1, well then here, if we don't pick Hey guys, Greg here. Today I wanted to talk about a very popular algorithm known as recursive.
It's another classic backtracking problem. We need to return all. I used to always struggle with backtracking. problems on LeetCode. When I saw it in the problem tags, I would literally just skip the problem. But last year, I locked in so hard, I went from 0 to 41 backtracking questions solved in just 1 week. Today, I'll teach you the template I use to do this so you could do the same. I'll also teach you how to identify backtracking problems and common mistakes to avoid. Let's begin with the definition. Trust me, we'll get to the code in a bit. Backtracking is a problem-solving technique where you explore possible paths for a solution step by step. Once you reach a dead end, you backtrack, which means you undo your last step and you try to find something else. I know you guys have all probably heard this analogy a million times, but imagine you're in a maze. You make a turn and you hit a dead end. So you walk back, pick a different turn, and keep repeating. Eventually, you find your way to the exit. This is exactly how backtracking works in code. This sounds great in theory, but it didn't really click for me until I began to visualize every backtracking problem as a decision tree. Here's what I mean. Every time you make a choice in a backtracking problem, like picking a number, placing a queen, or selecting a letter, you're essentially moving down the branch of a tree. At the top, you have your starting point, an empty answer. Each level of the tree represents a decision point, and each branch is a possible option you could take. The absolute most important question to understand for recursive backtracking is the subsets problem. If you get this, everything else starts to make way more sense. The question states, given an integer array of elements, return all the possible subsets. A subset is any combination of elements from the array. The order doesn't matter, we just need to group them. Say our input is an array with the elements 1, 2, and 3. For each number, we have exactly one decision. Do we include this number or do we skip it? At the first level, index 0, you decide, am I going to include 1 or not? If the answer is yes, we add it to the path and we move to the left. If not, we don't add it to the path and we move to the right without it. Now we're at the second level. We decide, are we going to include 2 or not? If the answer is yes, we add it to the path and move to the left, and if not, we don't add it to the path and we move to the right without it. Now finally, at the third level, we repeat the same step. Now here's the magic part, the backtracking. Let's say we just finished exploring the path 1, 2, 3. What do we do after we save this result? We need to explore other paths. So we rewind. We remove the 3 that we just added, and our path becomes 1, 2 again. We're literally undoing our last choice so we could try the alternative. From the path 1, 2, we can now explore the option where we skip 3, giving us the final subset just 1, 2. Then we backtrack again. We remove the 2, and we explore all the paths that include 1 but don't include 2. This is why it's called backtracking. We're constantly undoing our decisions to try different combinations. This is the code for the subsets problem. Let's walk through it line by line. I promise it's simpler than it looks. We begin by defining a helper function for our recursion. We pass in our index, which tells us which number we're currently deciding on. We also pass in our path, which is the current subset we're building. It's just a list. This is our base case. If the index equals the length of the list, that means we've considered every possible number. We're at a leaf of our decision tree. We add a copy of our current path into our answer array. The reason we append a copy of our path rather than just the path itself is due to the nature of lists in different programming languages. Since lists are passed by reference in Python and Java, if we didn't make a copy, we'd end up with a result list full of empty or incorrect subsets. Now this is decision 1, where we include the current number into our subset. We add it to our path, then we move on to the next number by calling backtrack index plus 1 with our path. Finally, we pop it. This is the backtracking part. We're undoing our last choice. We're removing the number we just added so we could try the other option. Now we explore the other branch of the decision tree. This time we skip the number and move forward without adding it to the path. And that's it. All backtracking problems can be broken down into the same 4 components: the base case, choices, the constraints, and our backtracking step. This is the exact template I used every time I came across a backtracking problem. Write this down or try to commit it to memory like me. This template works for everything: subsets, permutations, even LeetCode hard such as Sudoku or N Queens. Let me show you. Let's run through 3 problems super quickly using our template and show you how this works. Please pause the video if you need to read the descriptions. For the permutations problem, we want to return all permutations of a list of numbers. Now, our choices and backtracking step are the exact same as the subsets problem. We just want to pick some number, add it to our path, and pop it when we're done.
I just had like a very good idea.
However, this time we have a constraint. We can't reuse the same number more than once in our path. Now, we really didn't talk about constraints in the subsets example, and that's on purpose. Subsets was the perfect intro because you want to generate all possible combinations, but in most problems you don't want all of them, you only want the valid ones, and that's where the constraints come in. This ensures that we don't waste precious time and memory continuing down a path that's already not valid. However, as you can see from the code, it is very logically similar to the subsets problem and follows the template I showed you. By the way, the template is in the GitHub link in my bio. And if you already feel like you've learned something from this video, I would really appreciate it if you could subscribe. Now let's move on to combinations, another classic backtracking problem. We need to return all the possible combinations of k numbers in some range. This is extremely similar to the subsets problem. We just need to limit the subset size to exactly k, which means all we have to do is modify our base case a bit. We save our path to our answer array if the length of it is equal to k. And that's it. That's another backtracking problem farmed. This is how easy it is to modify your backtracking strategy using the template with just one line of constraint or base case logic. Now I know what you guys are saying. Oh, but you can't do a lead code hard. Yes, you can. Let's do the legendary end queens. We need I feel like anytime you watch a lead code tutorial, they never teach you how to recognize the problem pattern on your own. They just assume you'll know it. In fact, there are no tutorials on YouTube on how to recognize these patterns. If you search for advice on Reddit, everyone tells you to just gain the intuition. Well, how the
Yeah, I think you're supposed to just gain the intuition.
If you see a prefix tree problem on your coding assessment, it should literally be 3 points. I'm not joking. Prefix trees are the easiest data structure in the world. There's basically only one pattern that allows you to solve like 99% of all lead code problems. After spending hours figuring out this technique, I was able to solve almost 20 prefix tree problems in 1 week. In this video, I'll teach you that same pattern step by step, and then walk through how to identify prefix tree problems. We'll also walk through how to apply the pattern using some real lead code questions. I've also attached a free PDF guide of everything I've learned for you to save and review on your own. Let's begin with the definition. Prefix trees, which are also known sometimes as tries, are just ways to store sequences efficiently in a tree format. These sequences could be of any type. They could be integers, booleans, but for 90% of questions, we're looking to store sequences of
pick 2, then we end up with still just 1. And if we do pick 2, then we end up with 1. And then
No, I don't need this. Let's look into this. Backtracking MS, but limited in specific application. AI for puzzle solving, Sudoku type stuff. Games, chess/go, move, exploration, maze, pathfinding. Okay, chess is in chess.
then 2. We always just place that new number
of characters, which we just call words usually in English. Each node in the tree represents a single character in the word. Starting from the root, you move down one level for each character. If multiple words share the same starting letters, they share the same path down the tree. So for example, the words cat, car, and cart all start with C-A. In a prefix tree, you don't repeat C and A 3 times. You write it down once and then branch into T, R, and RT. This allows you to search for words by prefix in linear time. So instead of scanning every word, you just follow the letters down the tree. For example, if you want to check whether a word like car exists, you follow C to A, then A to R. This is linear time. Or let's say we want to find all words that start with the letter C and A. We would first follow C to A, and we could see that cat, car, and cart all branch from the same parent node. Now this is a very simple example that we all have probably heard in Data Structures 101, but to me at least it seemed very abstract to implement in code. But actually, it's very simple. Once you learn how to write your first prefix tree, you could essentially reuse the same code to solve any problem. All it takes is a bit of tweaking. Now, prefix trees only have two main operations, insert and search. Insert is how we add a word into the tree. So starting from the root, we check each letter one by one. If the letter doesn't exist yet, then we create a new node. If it already exists, we just move down to it. Once we reach the last letter, we mark that node as the end of a word using the end of word boolean. We could implement this in code using a class called try_node. So each node will have two variables. It'll keep track of its children and whether or not it's the end of a word. Here's a basic version in Python and Java. All of this code will be in the PDF guide in the description for you to follow along with and also just review on your own time. So like I mentioned, our try class has two main parts. The first one is an array called children. This is a list of 26 slots, and if you're wondering why 26, it's one slot for each lowercase English letter. Our try_node class also has a boolean flag called end of word. This tells us if a word actually ends at this node. So when we insert a word, we start at the root. For each character C, we calculate its index with C minus A, and A is in quotes. What this is basically doing is mapping the ASCII value of the lowercase letter to our children array. Put a little more simply, this is basically mapping A, like the character A, to index 0, B to index 1, and so on. If there's no child at that slot yet, we create a new try_node. Then we move down to that child and continue with the next character. We repeat this process for all the characters in our word. After we finish the word, we mark the last try_node's end of word boolean to true. That's how the try actually knows if a complete word stops here. So for example, if we're inserting the word cats into this prefix tree, we start at the root and then check if the letter C exists in the children array. It does, so we move down. Next, we check if the letter A exists, move down, then if T exists, and then move down. However, we could see that the letter S is null at this point. So we create this node, move down, and mark the end of word boolean to true. That was the insert operation. To search for a word, we again start from the root and walk letter by letter. If at any point the character slot is null, that means that this word isn't in the tree, so we return false. However, if we make it all the way down to the last character, then we return whether or not end of word is true, meaning this exact word exists. We use the end of word boolean because a word like cart might exist, but that doesn't automatically mean that car exists. We never actually inserted that exact word. The end of word boolean makes sure we only return true for words we've explicitly inserted. Now here's a little extra. Some LeetCode questions will have you check whether or not the prefix of a word exists, not the full word. For this, we can implement a function called startsWith. It's basically a copy paste of the search function. However, this time we're not concerned with the end of word boolean. If we can simply follow all of the characters, then we just return true. Here's one last method if you really want to master the prefix trees. Sometimes you want to get all of the words that share a prefix. For example, in autocomplete features or in word search problems. For this, we could use a depth first search starting from the last node of the prefix. So we go down to the last node as usual, then we explore all of the branches recursively, collecting words whenever we hit a node with the end of word equals true. And while I'm not going to go into depth on depth first search in this video, this is just an extension of the same pattern we already learned. You follow the letters down, and then instead of stopping at the end of the prefix, you explore every possible path below it using DFS. And that's it. Every prefix tree problem you'll ever see is just a variation of the same pattern. If you could nail this foundation, you're set. Now here's my challenge for you. Go and solve lead code number 208, implement try. Don't just watch, rewind if you need to, take a look at the PDF and actually code it yourself. If you can
Hi everyone. In this video, we will be going over the backtracking algorithm. Backtracking solves problems that involve exploring various
Okay, so to be honest, I kind of didn't have a plan for this video, but I was thinking, what topics could we address? And I mean, one of my favorite topics and one topic that a lot of people have questions about is the topic of backtracking and utilizing recursion to express a certain decision space or express possibilities. So what I really want to do with this is give you the toolkit, give you the blueprint that I don't know how this came to me, but it just came to me from doing a bunch of these problems. The toolkit and the patterns you can apply to these problems, and I mean it's recursion in general, but specifically for backtracking problems, the blueprint you need to apply. So what I thought up was something I always call the 3 keys of backtracking. I've done many backtracking videos, right? There, and also here and here and here. So I've done a good amount of backtracking videos. I mean, but they're a while back, and I mean, my video quality was pretty bad. I didn't have a mic, and I kind of want to re-dive into this and actually explain it again. So why not? So what are the 3 keys to backtracking? I actually addressed this in I think my favorite video, my N Queens video, which is a while back. I also did not have a mic. The quality wasn't the best, but that was one of those original videos that goes a while back. What I talked about is the fundamental keys to backtracking problems. It goes like this. You make choices, you have constraints on those choices, and at the end you're going to converge towards a goal. You have a decision space you can choose from. Your decisions are restricted somehow. And your goal is somewhere. Your goal is to do something. Maybe it's to fill a string. Maybe it's to fill n slots. Maybe it's to solve a Sudoku board. Our goal would be to solve this. And what we need to do is see how each of these influence how we shape our code, how we shape our approach and the way we think about these problems, and see how we can decompose something that's intimidating, like solving a Sudoku board, which is the example we'll do. I already did a video on solving Sudoku, but we'll run through this as an example to demonstrate these concepts that I'm trying to get across. So why don't we get into it? We have our choice, we have our constraints, and we have our goal. Says, okay, write me an algorithm that solves this. I have no idea how to do this. Do I use 2 for loops or something? Do I just go through this? So what we need to fundamentally think about is the core choice. The core choice that we are making at each step. This is how we can craft a recursive function to solve a problem like this. So we have a Sudoku board. And yes, that's a Sudoku board. It's a lot of stuff. We don't know how to start with this. But I would say that we do know how to start with it because we know the choices we're we're making. What we need to do is we need to fill these cells. We need to fill those cells, right? And we need to fill those cells by making choices. So I said a key word there. I said a cell. So our key choice will be made on a cell. So, okay, where does a cell sit? Well, a cell sits in a row and it sits in a column. So, okay, I have a lead. I have a lead on how I can draw a function. So I'll call my function solve, and I'll pass in a row and a column, and the job of the function will be to solve that specific row and column. Well, my next question is, how do I solve a cell? How do I actually do the process? So let's reduce our decision space. We have a big Sudoku board. Why don't we get rid of every row except the first row? So the way we need to think about this is we need to think about this compartmentalizing into subproblems. So we want to solve cells, and when we solve all the cells in a row, then we focus on the next row and the next row. And by the time we finish every row, we will have finished. But we'll get to the goal part later. So our choice at every single cell is going to be to place a number. What are the numbers we're able to choose? We can choose these guys. We can choose numbers from 1 through 9. So our decision space that we can choose from is going to be from 1 to 9. So let's bring back that code snippet. We're working on that code snippet right there. We're trying to solve for the row and column. But what do we do inside? Well, I know I have a decision space. I can place numbers 1 through 9 in the cell if it's empty. If it already has a number, then I don't want to place a number there. But if it's an empty cell, why don't we run a for loop? So let's put a for loop right there, and there's our for loop. It runs from 1 to 9. I express my decision space. We're making progress. We're not lost anymore. We know what we're doing so far. So we saw a large Sudoku board. We broke the problem down into solving a cell. We're slowly crafting our recursive function, and we're slowly getting there. So what we now need to think about is when I solve a cell, I can place an item. So once I place an item, it would kind of look like that. So if I place an item, it's going to look like that, and we're going to put an item in the cell. And so now I've made a choice, and now I need to express my constraints. What are my constraints? So the thing is, when we place an item, I could validate the whole Sudoku board, but that's a waste of time. That would be to the order of n squared, and we don't want to do that. All we need to do is we need to validate the row, we need to validate the column, we need to validate the subgrid that the number we just placed sits in. So if I place a 2 here, if in my for loop says, okay, put a 2 there, all I need to know is, does the 2 break the row? Does it break the column, and does it break the subgrid? So again, I already have a video on the Sudoku solver stuff, so I don't really want to go into those logistics. I really want to talk only about backtracking here. So okay, so the key here is, what we need to do is, if that was a valid placement, I recurse on it. So why don't we put our recursion right now? Do you see that? We recurse on our decision. So we recurse on our decision, we'll do some exploration, but do you see what I called it with? Why did I say column plus 1? Well, I mean, think about it. If we solve this column, what's the next logical step? We solve the next column, and then the next. So my function is a policy. My function is a policy that is going to know what to do based on the state that it gets input. So imagine this. If I am at the end of this row, right over here, if you pass me a column that is out of bounds, and I am not at the final row, what is the natural decision of the recursion? Well, the recursion is going to say, well, just solve this cell over here. Go to the next row, start in the first column. So that crafts a base case. So this gets me to our goal. So our goal here is to reach our base cases. So one base case is where we finished a row and we overbound, we out of index on the row, and we need to go to the next row. That's one base case. And the final base case is when we're down here. The final base case is when I out of bounds on the final row. When I go out of bounds on the final row, that means every row is finished. If I go out of bounds here, then that means there's more rows to finish. It's not our final row. But if it's our final row, and we just finished it, that means we finished. And that crafts our base case. So let's move all our decision space stuff down a little, and let's put our base cases right there. So what we need to see here is we're slowly understanding subproblem down, craft my decision space, adhere to my constraints, converge to a base case, and now what we need to do is we need to keep in mind, what if a decision doesn't work out? So if a decision does not work out, once we come back from our exploration, we need to eject our decision. And we can put that right there, and it's right there. That's how we remove our decision. We just remove it from the cell we placed on. So this is how it works. We craft our function based on our choice. We have base cases we converge to. We have a decision space, and we undo our decisions after we explore on them. And what we do is, at each of these calls has a goal, and it tells us, was the Sudoku solvable given the placements that we just did? So these are the keys to backtracking. The choice you make. What is the fundamental subproblem? What is the core decision space? This is our decision space for a cell. Our fundamental choice is choosing from this decision space what we want to express in the cell. Once we express that, we recurse on that decision. If the decision doesn't work, we come back and we undo it and we make another choice. We explore, we undo, we make another choice. So bring the code back right there. That's what our for loop is for. Our for loop is for exploration within the stack frame. This cell needs to explore 1 through 9. This cell explores 1 through 9. This cell explores nothing. It already has a number. This cell explores 1 through 9.
Let's
Let's
do
do
trees.
trees.
I
I don't know. I'm thinking whatever easy problem that I never did. Stack, heap, kth largest element in a stream. Okay. Design a class. Oh, bro. Nah. Too much. Too much. Give me some actual easy problems. last stone weight. Okay. You're given an array of integer stones where stones I represent the weight of the ith stone. We want to run a simulation on stone. What the hell? I did not do this. So this is the heapify. Oh, actually remember heap. Wait, actually remember heap. No way. So what is going on? Fuck. Bro, that's the most retarded thing ever. Opens up a front-end masters. Finally. Okay.
All right, we are now going to start this.
Let's go heap.
Back in. We just got done doing a binary search tree. We did the actual finding of it. We explained how insertion and deletion, some of the problems that go with it. We're back in. We're feeling ready. We're very, very, very excited. At least I am super excited. And then I forgot to do this. We already talked about that, actually. We did do all that. So we're going to move on to our next structure. No, we're not going to be doing any balancing of a tree because, of course, like I said, it's a very long operation. And I think that if we were to do a follow-up course with this, we'd probably cover things like binary or, tree rotations and other fun trees that we're not covering here. So I always make this joke. If you just say the word priority queue, I'm going to hire you in an interview. I just want to hear you say that phrase because those things are useful. I know it's a joke, but it's like not a joke, but it's definitely a joke. But it's not really a joke. And so this is a very important data structure. It's often referred to as a heap or a priority queue. And the simplest way to put this is that it's a binary tree in which every child or grandchild is smaller, that's called a max heap, or larger, that's a min heap, than the current node. Meaning that whenever a node is added, we must adjust the tree. And whenever a node is deleted, we must adjust the tree. You don't traverse this tree, though we could traverse the tree, you don't traverse the tree. And it'd be actually extremely simple to traverse it in breadth first ordering. So let's you don't even need a data structure at that point to do it. It's already in that order. So let's first go over what a heap really is. I'm going to restate it, but this time with sweet circles and arrows. So I'm just going to put a value, 50. Let's start with a min heap. So a min heap means that the top value must be the smallest. Obviously, if you have duplicates, say we had more 50s, they could be children of 50. That's just fine. But that means both of these must be larger. So I can put something like 71. I can put something here like 100. Now here's where the ordering gets a little bit goofy. I can have children here, which they have to be larger than 71. So we can put it, say, as 101, and we can put this one as 80. Right now, you're probably thinking, well, shouldn't that be right there? Well, no, it shouldn't be right there because heaps maintain a weak ordering, meaning that they are ordered, but it's not perfectly ordered, right? It's not in order of anything specific, but there is a rule at every single point. And so if we were to do some right here, we could have 200, and we could also have 101, right? It is fine, just long as it keeps on getting larger as we go. And so what this is called a heap condition. The heap condition effectively states, if it is a min heap, that every node below me must be larger than, or technically equal to. If it's a max heap, it states that every node below me must be smaller than or equal to, because obviously a max heap means the maximum item is the root. A min heap means the minimum item is the root. And so this means if we needed the smallest item out of this tree, well, it's really simple. It's right there. It's at the tippy top. We could grab that item, or we could peek it at least at O of 1. So it's super, super fast to be able to inspect and say, that's the smallest item. Obviously, we couldn't get the median very easily right now because we don't actually have that available. There is a trick to get the median if you use 2 heaps. We're not going to do that. It's a stupid Google interview question. It doesn't really show you anything other than you can say the word priority queue. All right. So now that we have that, let's think about how we would add a node to this tree. Now, one condition I didn't say is it always complete like this? Yes, a binary tree or a heap is usually full or complete tree, meaning that it's always adding from left to right and it never has any empty spaces. Like that would never exist in a heap because that is an empty space, meaning there is nothing on the left-hand side. That just does not exist. So every single node is filled in from the left to the right, always.
So where does it actually use?
Back in. We just got done doing a binary. This becomes 101.
Oh, low-key essential. They have low-key essential, okay.
This becomes 3. We do it again.
Give me a question, bro. So stones, okay, we just, it's a max heap. I think you're doing it because binary search sorting. You're doing this because it's a max heap. We need a max heap. So first is equal to heap. So we got the heap. We heaped everything. Okay, length. So meaning it's starting from that end. So the first is equal to what? Heap queue, heap pop. So we're popping the. No. What? So the second iteration, we're gonna pop. What the hell? What? I don't. So let's go first. Yeah, it's just like forget the negative 6 minus 3. Yeah. First, if first is bigger than, okay. Append. What the hell? Bro, why did I do this? Makes no sense. Shit. I need to go heap.
Am I smaller than my parent? I am. So this becomes 3. This becomes 71. Am I smaller than my parent? Yes, I am. Now the root becomes 3, and this one becomes 50. Is our heap now correct? Yes, it is. And we can do this again. We can simply add to the next spot and do the same bubbling up as we go. Let's just say we added 200, and so we don't have to do any bubbling at all. We're good. We're larger than our parent, so therefore we do not bubble up. Awesome. But what about deleting? Deleting is, we do have one question.
Sorry, is this a doubly linked list implicitly then? or how would you establish the relationship between 100 and the new root node?
So the question was, is this a doubly linked list implicitly, or how's it, what's happening? How do you establish that parent-child relationship? The answer is sort of. I'll show you here in a moment. We'll get there because it's that part is just like, right? It's fantastic. So it's going to use a data structure we've already created as our backing data structure. We only just simply understand it in a certain way. It's beautiful. All right. So how do we delete? We have 3 at the top. We want our most minimum item out of this heap. Well, let's go like this. We now remove 3. We're gonna return 3. But now we have a hole in our tree, right? The top node is empty. So what do? Well, we take our very last node in the tree, we delete that out, and we put it at the top. Now we need to heapify down, right? So we bubbled it up or heapified up. Now we need to heapify down to put it back into a correct spot. So what do? Well, since we're using a min heap, we're gonna want to take the minimum of the 2 children and compare against that. So what's smaller, 50 or 100? Clearly 50 is smaller than 100. So is 200 greater than the smallest of our 2 children? Yes, it is. So let's swap. 50 takes its rightful place as head of the queue. 200 goes here. We do it again. We take the smallest of our 2, which is 71 or 81. It's 71. So we do it again. So let's do that. So is this thing larger? Yes, it is larger. So swap. 71 makes it all the way up here, and 200 goes right here, or equal to. All right, that's pretty fancy. So now, hopefully, if you've been following along thus far, you're probably thinking, that sounds great and all, but how the hell do you get this node, right? I'd have to traverse my tree to know where the next node needs to be added, right? It'd actually be really, really hard to know that answer, given how we built trees thus far, which is like a node-based data structure, correct? Yeah, it would be really, really hard. So let's not do that. Let's not do that at all. We need to kind of reimagine how we can store a tree. This is reimagining, by the way, and that's a light bulb going off. All right, fantastic. So let's put an index to each one of our nodes. So this one is 0, 1, 2, 3, 4, 5, 6. Okay. Do we see anything going on here? Do we see anything? Why start at 0? Wow, that sounds a lot like an array prime. That's because it could very well be an array prime. So let's think about this. If we could store this in an array, then 50 could just be in the 0th position, right? Then the next 2 children, which is 71, and what's the other side? 100. This side, what's that one? 101, 80, 200. Oh no, running out of space. 200, 101, and then I think the last one, which I forgot to put a number by, which would be 7, would be right here. 200 again. So look at that. 0, 1, 2, 3, 4, 5, 6, 7. 7 for 200, 7 for 200. That worked out. We were able to put it correctly into an array.
This would be implemented in an array?
This would be implemented in an array. So we'll keep on going. We're technically going to implement in an array list. You can see right here in just 1 second. Because that way it's growable, or you have to build an array list, a growable amount. Because you don't know how many items are going to be in the heap, right? So like you keep on inserting items, you're going to have to keep on growing the underlying data structure. So great, we found a way to store it. But now, the obvious question, how do you do parent-child relationship, right? There is no next, there is no previous, there is no left, there is no right, there is no parent. How do you do it? All right, well, I'm pretty sure we could come up with a formula to be able to do this. So we could do this fun game where we try to guess our way there, or I can just tell you. So let's just look at this one right here. 2 has a child of 5 and 6. So I can say 2 multiplied whatever my index is, plus 1 is the right-hand side, correct? 2 times 2 is 4 plus 1 is 5. I can do 2i plus 2 to be the right-hand side. 2 times 2 is 4 plus 2 is 6. But you're saying, I don't know if this shenanigans really, does it really actually pan out? So that'd be 7, 8, 9, 10, 11, 12, 13, 14, right? That would be the next set of children in the placement if we were to do that. So 6 would have a children of 13 and 14. So let's find out. 6 times, or whoopsies, it's not I. It'd be 2 times 6, because that is I, plus 1 should be equal to 13. Simple fraction, 13. 2 times 6 plus 2 should be equal to 14. It's 14. Awesome. Look at that. We just found a way to map ourselves into our children's area, right? I don't know how to describe that. We've traversed to our children, right? That is actually pretty dang incredible, because that is, there's no links, right? There's no management of links. So in some sense, it makes management of this data structure way, way easier, because you don't have to be like, okay, my parent, I got to delete, oh crap, I deleted the wrong one, all my data's gone, okay, let's rework this, right? You don't have to do any of that, because it makes it so much simpler. But we still have a problem. We have solved the generic case for going downwards, but we haven't solved the generic case for going upwards. So 2i plus 1, 2i plus 2. Now, we could go like this. Okay, if my index is odd, therefore I could do a left-hand equation to jump up. Or if my index is even, I could do a right-hand equation. I just picked the number, I don't actually know. Oh, it's true. It's true based on him. That is right-hand side. Perfect. So that would have worked out. We could do some sort of like case statement for the parent, but we don't actually need to do that. We can think of it as a single equation. Now, in real programming languages that aren't JavaScript,
this is actually good. I need to use this side by side. Use to cracking the interview side by side. And next thing I'm going to do, I'm going to max out the trees. Let's look at trees. Let's open up the trees. Trees traversal, trees implementation. Okay, let's get some basic down on trees.
Linked lists, arrays, searching, sorting.
Yeah. So trees. I don't think I need the linked list. It's fun, but it's like, yeah, it's using a dummy number and all that. It's kind of confusing.